Hello and welcome back. In this lecture today, we're going to look at a quantity called as fugacity. Fugacity comes from a root word which means the tendency to escape, and this has been developed to characterize vapor-liquid equilibrium in an easier fashion. Before we get into details of fugacity, let us quickly revise what we have done so far. We're looking at solution thermodynamics or thermodynamics of mixtures of chemical species. We talked about partial molar properties. We talked about how the total property of a mixture is related to the partial molar property. We looked at properties of ideal gas mixtures, and we also defined an ideal solution which has similar characteristics as that of an ideal gas mixture. For example, G for an ideal solution is same as its counterpart for the ideal gas mixture. So G for an ideal solution is sigma yi G I for the pure species plus RT sigma yi ln yi. And based on this, we can derive the other thermodynamic properties such as the entropy for an ideal solution, enthalpy, and volume for an ideal solution, as well as we have defined a host of other thermodynamic properties such as property changes upon mixing, etc. In addition to this, in the previous lecture, we have also looked at a quantity known as an excess property, which is essentially the deviation from the ideal solution behavior. We defined it as, for any thermodynamic property, we defined it as M minus M ideal. We also looked at the fundamental property relations in terms of Gibbs free energy as the generating function. dNg by RT we said is NV by RT dP minus NH by RT square dt plus sigma over I. Let's write it as Gi bar by RT dNi. In addition, we can also write similar equations for the residual Gibbs free energy. All the quantities change into residual quantities in this case, and we get this by subtracting an analogous equation for ideal gas plus sigma over I Gi bar R, which is partial molar residual Gibbs free energy dNi. And if we subtract the ideal solution equation from this, what we get is dNge by RT from the first equation, of course, is NVE by RT dP minus NHE by RT square dt plus sigma over I Gi bar E by RT dNi. And based on this, we can write a host of derivatives such as derivative of Ng over RT with respect to temperature will be negative NH by RT square, and so on. Of course, that derivative is taken at constant pressure and composition. So we looked at the similarities between the residual properties and excess properties, and we also talked about the nature of excess properties. We said at the pure component limit xi going to 1 ME, the excess property should go to 0 because it will hit the pure component limit. Both M and M for the ideal solution approach the pure component limit, so that difference will go to 0. This is true at all the corresponding pure component limits for each of the species. In addition, we also said that there is no other thermodynamic restriction for variation of GE or HE with composition. We have seen that GE can be positive or negative depending on whether the system has positive deviations from ideal solution behavior or negative deviations from ideal solution behavior. We also said that HE can be greater than or less than GE. It can be a positive quantity, negative quantity, and it can have a wide variety of behavior, as we have seen in the previous lecture. Now, the task in front of us is to be able to characterize the behavior of mixtures or solutions, and to be able to do that, we have introduced a quantity known as excess quantity, which is essentially the deviation from ideal solution behavior. And to be able to characterize excess quantity, we want to use Gibbs free energy as the generating function, or GE as the generating function. And if you recall, in the last class we said GE is obtained from vapor-liquid equilibrium experimental data. It is obtained from experimental data for vapor-liquid equilibrium. In addition, HE is obtained from mixing data or experimental data for mixing of two chemical species. If that be the case, to be able to understand the behavior of systems which are not ideal, we want to quantify the excess quantity or excess Gibbs free energy, we need to understand the vapor-liquid equilibrium behavior of substances or a mixture of substances. So to be able to do that, let's quickly recall what we discussed about vapor-liquid equilibrium. We said when there is two phases that are in equilibrium with each other, then the chemical potential for each of the species in the two phases, alpha and beta, needs to be same. And this is true for all the chemical species I that are present in the two phases. And this characterizes equilibrium in addition to the equality of temperatures in both the phases and equality of pressures in both the phases. Talking about a vapor and liquid equilibrium then, and if we have two components, then mu1 in the vapor phase should be equal to mu1 in the liquid phase. Mu2 for component 2 in the vapor phase should be equal to mu2 for component 2 in the liquid phase. This is for a binary system of two species in equilibrium, VLE for a binary system. Now, I can write chemical potentials also in terms of partial molar Gibbs free energies. This also means that G1 bar in the vapor phase should be equal to G1 bar in the liquid phase, and G2 bar in the vapor phase should be equal to G2 bar in the liquid phase. Let's take a minute and look at what G1 bar and G2 bar in the vapor and liquid phases are, in any phase for that matter. If you recall, for an ideal gas, G1 bar for an ideal gas was G1 for the ideal gas of the pure species at the same temperature and pressure plus RT ln Yi or Y1. So G1 Ig will be gamma 1, some constant for that species, plus RT ln P. And G1 bar Ig then will be gamma 1 T plus RT ln Y1 P. And for any species I, of course, this will be GI will be gamma I T plus RT ln YIP. As pressure goes to 0, the only way this equation will be satisfied is if this partial molar Gibbs free energy, Gi bar Ig, goes to negative infinity. Only then this particular equation will be satisfied. So this is true in general for any chemical species. The limit at 0 pressure, both Gi bar Ig, hence the chemical potential mu I Ig, will approach negative infinity. So in that sense, chemical potential is not a convenient function to use or easily relate to. So what we rather do is try to define a quantity which is not so abstract, and to be able to do that, we resort back to the equation we started with. dGig or dGi bar Ig is RT d ln YIP. For an ideal gas, this equation is true. What we do is, for a real gas, we will write an analogous equation. dGi bar for any gas, or for any substance for that matter, not just gas, is written as RT d ln Fi hat. So what I'm doing is replacing the partial pressure in the ideal gas, Yi times P is the partial pressure Pi, with a quantity called as Fi hat. The hat is the hat I put on top of Fi, of course, right? Fi and a hat, and it indicates that we are talking about the quantity F in a mixture. F for species I because of the subscript I, and this quantity F is what we call as fugacity. And like I said at the beginning of this lecture, fugacity generally means the tendency to escape, and in relation to vapor-liquid equilibrium, as we will see, greater the fugacity, greater is the tendency of that species to stay in the vapor phase, and hence the name. So this is the definition for fugacity of species I in the mixture, and to be able to complete the definition we need to define a limit, and that limit turns out to be the limit at the zero pressure. We say that at limit as P goes to 0, Fi hat will be Yi times P. It will approach the ideal gas limit. That is how we complete the definition for fugacity of species I. So these two equations right here put together define the fugacity of species I in the mixture, which we are calling it as Fi hat. We use a hat instead of the bar we have used for partial molar properties, such as partial molar Gibbs free energy here, because Fi hat is not a partial molar property, but we are still talking about a species I in the mixture. So differentiated from a partial molar property, we are using a hat instead of the over bar, as in case of partial molar properties. So these two relations here complete the definition for fugacity, right? And if you observe these two equations closely, the first equation is Gi bar, like I said earlier, can be written as some constant for that species I at the temperature of interest plus RT ln Fi hat. And for an ideal gas, I can write an equation because it is only dependent on temperature and the species, that constant is still going to be the same, plus RT ln Yip for an ideal gas. And if I subtract one from the other, what I get on the left hand side is Gi bar R, or the partial molar residual Gibbs free energy, and on the right hand side we have RT ln Fi hat over Yip, right? And this quantity here on the right hand side, Fi hat over Yip, is called as phi I hat. Corresponding to Fi hat, we have a phi I hat, which is the fugacity coefficient. It is essentially the ratio of fugacity to the partial pressure, and we call it as the fugacity coefficient. So what we have now then is two equations. One is dGi bar is RT d ln Fi hat, and Fi hat over Yip is what we are calling as phi hat. And in addition, limit of P going to 0, Fi hat is Yip, or limit of P going to 0, Fi hat over Yip is limit P going to 0, phi hat for the fugacity coefficient, and this value is 1, right? So the fugacity coefficient of species at the zero pressure limit is going to be 1. In addition to this, once we have written these equations for a mixture, we can also write corresponding equations for pure species. dGi is RT d ln F. F over P for pure species Yi is 1, so F over P is Fi over P is phi, and limit of P going to 0, Fi will be equal to P, and limit of P going to 0, Fi over P will be limit of P going to 0, phi, and it will still be 1. Now notice the analogy between the two. For a mixture or for a pure species, we have analogous equations, except that we are replacing the fugacity of species I in the mixture Fi hat with the fugacity of the pure species. I'm sorry, I should have written a I here, fugacity of the pure species Fi. And because it is a pure species, dgi bar will be same as dgi, and the fugacity coefficient will be phi instead of phi hat. So the equations are otherwise analogous. They will reduce to pure component equations as yi goes to 1, of course. In addition to this, what is the advantage of using fugacity for vapor-liquid equilibrium calculations? If we think about it, Gi bar is some constant plus RT ln Fi. And recall that Gi bar is same as the chemical potential mu I. Now, if I write these equations for the vapor and the liquid phases, then mu I in the vapor phase is gamma I, which is a function only of temperature. It will not depend on the phase, it will depend only on the species. As long as the species I is same, it will simply be gamma IT plus RT ln Fi hat, the fugacity of that species I in the vapor mixture. Similarly, mu I in the liquid phase is going to be the same constant plus RT ln Fi hat in the liquid mixture. And because at equilibrium mu I hat vapor is mu I hat, and because at equilibrium mu I vapor is mu I liquid, from these two equations what we get is Fi hat in the vapor phase, the fugacity of species I in the vapor mixture should equal the fugacity of species I in the liquid mixture. So instead of relating the vapor-liquid equilibrium via the chemical potentials, what we have achieved by introducing fugacity is that the fugacity of these species in the vapor and liquid mixtures are going to be same for a VLE. Right. So in that sense, we can probably easily relate to these quantities, and these quantities are well behaved even at the limit of zero pressure. As we have seen, the fugacities boil down to partial pressures. In a pure component, it is simply the pressure, etc. So we can relate to fugacity in an easier fashion than to chemical potential probably. If that be the case, to be able to characterize the vapor-liquid equilibrium behavior, we can work with fugacities provided we know how to calculate fugacities. How does one calculate fugacity of a species? So, by the way, to be able to calculate fugacity, let us go back to its definition and ask a question: what is fugacity of species in an ideal gas? So first, let's talk about fugacity of an ideal gas. Let us say we have a pure species in an ideal gas state. By definition, fugacity is dG is RT d ln F, and we want to calculate this quantity, and dGr or Gr by RT is ln phi, right? This is for pure species. We can use a subscript I, but because there is only one species, we'll just ignore the subscript. So the residual Gibbs free energy is related to the fugacity coefficient phi via this equation. For an ideal gas, Gr by RT is 0 because there is no residual property, which means that ln phi is 0, or the fugacity coefficient is 1. Because the fugacity coefficient is 1, F by P is 1, or F is equal to P for an ideal gas. This will hold because the residual Gibbs free energy for an ideal gas, of course, is 0. Now, if we have a scenario where the residual Gibbs free energy is not 0, if the gas is not ideal, so let's talk about a real gas. And we're still talking about pure species, but let's talk about a real gas which obeys virial equation of state. Then by definition, ln phi is gr over RT. I'm talking about pure species, so like I said, I am ignoring the subscript I. Ln phi is gr over RT, and if it obeys virial equation of state, if you recall how we calculated the residual properties, gr over RT was integral 0 to p, the compressibility factor z minus 1 dp over p. That was the relation for gr over RT, and for virial equation of state, z is 1 plus bp over RT using only the second virial coefficient, or z minus 1 is bp over RT. So this integral will then be bp over RT times dp over p. These two get cancelled. The second virial coefficient is function only of temperature. So I can take everything out of that integral sign because they are only functions of temperature. B over RT integral 0 to p dp, or this will be bp over RT. So gr over RT is essentially bp over RT using virial equation of state, or ln phi is going to be simply bp over RT. Once I have phi, I can calculate the fugacity coefficient if I know the pressure. So if I have virial equation of state and I know the second virial coefficient, then I can easily calculate the fugacity for pure species, right? Let's work on one quick example using this idea. We have a virial equation of state and we want to calculate the fugacity and fugacity coefficient for ethylene at 373 Kelvin, one temperature and three different pressures, 1 bar, 10 bar and 30 bar. And the second virial coefficient for this particular compound is given by the relations shown here. We first need to calculate two quantities, B0 and B1, which are related to the reduced temperature. And once I have the two quantities and I know the critical constants, I can go back and calculate the second virial coefficient. And throughout, as you can see, the second virial coefficient will only be functions of the reduced temperature or temperature and the critical properties, nothing else. So it will only depend on temperature for that matter. When the pressure changes from 1 to 10 to 30 bar, B is not going to change. So what we'll do is first calculate this quantity B so that I can then use it for all the three pressures. To be able to do that, we need the critical properties so that I can calculate TR. Let's use a suitable reference and obtain the critical properties for ethylene. Turns out for ethylene, the critical temperature is 282.3 Kelvin and the critical pressure is 50.4 bar and the eccentric factor omega is 0.087. Once I have these three, I can calculate the reduced temperature. It is T over Tc, or 373 over 282.3. So this will be 1.32. Then once I have the reduced temperature, I can calculate B0, which is 0.083 minus 0.422 divided by 1.32 to the power 1.6, and this value turns out to be negative 0.1872. Similarly, B1 is going to be 0.0856. And once I have B0 and B1, I can calculate B. It will be negative 0.1872 for B0 plus the eccentric factor 0.087 times B1, which is 0.0856, times R, which is 83.14 bar Cc per mole per Kelvin, times Tc is 282.3 Kelvin over Pc, which is 50.4 bar. And once we use these units, what we get is a value of B as negative 83.72 cc per mole. So now I have the value for the second virial coefficient from the given correlations. Once I have this value, I can use this B to calculate the residual Gibbs free energy, the fugacity coefficient, and hence the fugacity. If you recall, both the residual Gibbs free energy and ln phi are same, or residual Gibbs free energy gr by RT and ln phi are same, and they are equal Bp over RT for virial equation of state using only the second virial coefficient. And once I have the value for B, which is negative 83.72 cc per mole, I just need to be careful with the units. The pressure, we have three different conditions for which we are interested in calculating ln phi. The first one is 1 bar over 83.14 and 373 Kelvin, right? And for this value, it turns out that ln phi is 0.0027, and I take an exponential of that, we get phi, which turns out to be 0.9973, and F, if you recall, is phi is F over P, which implies F is going to be 0.9973 times the pressure, which is 1 bar. So the units for fugacity, of course, are going to be same as that of pressure. So that will be 0.9973 bar. I can do it at 10 bar, and the values I get are ln phi is negative 0.027 and phi will be 0.9734 and F is going to be 9.734 bar. I can repeat the calculation at 30 bar. Ln phi is going to be negative 0.081, phi is going to be 0.922, and F is going to be 27.67 bar. As you can see, once the pressure increases, we are moving away from zero, the ideal gas behavior, and hence the fugacity coefficient phi moves farther away from 1, and the fugacity itself, F, is going to move farther away from pressure P. And that is what is happening as we increase the pressure from 1 bar to 10 bar to 30 bar. This is how we can use a virial equation of state to calculate fugacity of pure species. Now recall, we have used Lee-Kessler tables to calculate the residual properties, the residual enthalpy and the residual entropy. So these Lee-Kessler tables also exist for calculation of fugacity and fugacity coefficient. If you recall, they are based on Pitzer correlations which arise from theorem of corresponding states. And we said species which are at the same reduced conditions, reduced temperature and reduced pressure with the same value of eccentric factor omega behave similarly. One of the ways we have used Lee-Kessler tables to calculate the residual enthalpy is by calculating HR by RT via two quantities, HR by RT 0 plus and HR by RT 1. Both these quantities can be obtained in two different tables at the given reduced conditions TR and PR, and then the total HR by RT was sum of these two, the second quantity of course multiplied with the eccentric factor omega. Similar tables also exist for calculation of fugacity coefficient. Essentially it is related to residual Gibbs free energy, right? So, and the way we use Lee-Kessler tables is again calculating two quantities and phi naught and phi 1, or looking up for two quantities phi naught and phi 1 in the Lee-Kessler tables at the given reduced conditions TR and PR, and then calculating phi, the fugacity coefficient using the relation phi is phi naught phi 1 times phi 1 to the power omega. Actually, what it is ln phi is going to be ln phi naught plus omega times ln phi 1. Ln phi, of course, is the residual Gibbs free energy gr by RT. So we combine them with omega, and then if you get rid of the logarithms, what we end up with is a relation like this. So this is how we're going to use Lee-Kessler tables for calculation of fugacity coefficients. Let's try to solve this particular problem using this idea. We're interested in calculating the fugacity coefficient again for ethylene at 373 Kelvin and 30 bar. At these conditions, the first thing we have to do is calculate TR and PR. If you recall, in the previous problem we said TC for ethylene is 282.3 Kelvin, PC is 50.4 bar, and omega is 0.087. And what this means is TR is going to be T over TC, it's going to be 1.32. PR is going to be P over PC, which is going to be 0.595. At these conditions, in fact, it is 1.321. And at these conditions, we are interested in looking up the Lee-Kessler tables for a value of phi naught and for phi 1. As usual, Lee-Kessler tables are listed at discrete steps. The ones I have used, the reduced pressure, it is listed at 0.4 and 0.6. For reduced temperature, it's listed at 1.3 and 1.4. What we're interested in is something in between 1.321 and 0.595, right? So if you recall, we need to do a double linear interpolation. So first let's write what we have at the conditions listed in the table: 9419, 0.9141, 0.955, and 0.933. We can do a double linear interpolation and end up with a value of 0.9188. This is for the quantity phi naught. This will give us a quick estimate. If we want to do a more rigorous calculation, we will also involve phi 1. I look up for these 4 values in the table and then do a double linear interpolation. And once I do that, I will end up with the value of phi 1 at the desired conditions. Right? So these are the 2 quantities I'm looking at the desired conditions, phi naught and phi 1. I will combine them using the eccentric factor omega to get phi. 0.9188 times 1.0411 to the power 0.087, and this value turns out to be 0.922. And once I have phi, F is going to be phi times the pressure, and in this case the pressure is 30 bar, so it will be 0.922 times 30, which turns out to be 27.66 bar. So using the tables, we can also estimate fugacity of the pure species. So we have looked at virial equation of state to estimate the fugacity of pure species. We have used the Lee-Kessler tables to estimate the fugacity coefficient and hence the fugacity for pure species. When we come back in the next lecture, we'll look at how to estimate fugacity coefficient using cubic equation of state and then extend this discussion to a mixture of chemical species. Thank you.